Welcome everyone. I'm excited to kick off this presentation. Today we'll be exploring the fascinating topics of work, energy, and power. This is the first slide, so I just want to give you a quick overview. We'll cover the fundamental concepts, their relationships, and how they apply in real-world scenarios. Let's get started. Let's start by understanding how work is done. Work occurs when a force is applied to an object, causing it to move or change in some way. This concept is fundamental because it links force and motion directly. Moving on, we see different types of work, such as work done by gravity or by applied forces, each with its unique characteristics. Next, we explore the types of energy, which include potential energy and kinetic energy. Potential energy is energy stored due to an object's position or configuration, while kinetic energy is the energy of motion. These two forms are central to understanding how energy is conserved and transformed. Speaking of potential energy, we have gravitational potential energy, which depends on an object's height and mass. The derivation of its equation helps us quantify this stored energy precisely. Similarly, for kinetic energy, deriving its equation allows us to understand how an object's motion relates to its energy. Now, let's look at elastic potential energy, which is stored when objects are stretched or compressed, like a spring. This type of energy is important because it demonstrates how elastic materials can store and release energy efficiently. Moving forward, we examine the general concept of energy itself, how it flows and transforms within systems. Power, on the other hand, measures how quickly work is done or energy is transferred, emphasizing the rate of energy change over time. Finally, we will see some real-world examples of work, illustrating how these principles apply in everyday situations, tying everything back to the overall theme of energy and work in physics. Work is done. When we talk about work in physics, it's essentially about energy transfer. It all starts with energy, which then relates to force and ultimately connects to the concept of a function. Now, on this slide, we're focusing on the question, how is work actually done? Think of it this way. For work to be done, there needs to be a force applied to an object, and that force must cause some displacement. It's not just about pushing or pulling randomly. The force must act in the direction of the movement for work to be positive. This is a key point because it links force and displacement directly. The amount of work depends on how much force is applied and how far the object moves in the direction of that force. By understanding this process, we can see how energy is transferred from one form to another. So, in essence, work is the mechanism through which energy moves, whether it's lifting an object, moving it across a surface, or even accelerating it. And that's how work is done. It's a fundamental concept that helps us describe a lot of physical phenomena in a clear, measurable way. When we talk about work in physics, it's important to understand that it involves force, displacement, and the angle between them. The formula W equals F cos theta times d illustrates this clearly. If the force makes an angle theta with the direction of motion, we only consider the component of force that actually acts in the direction of the displacement, which is F cos theta. This component is what does the work. The SI unit for work is the joule. Abbreviated as J, it's a measure of energy transfer. Remember, work is a scalar quantity, meaning it has magnitude but no direction. You can think of work as the transfer of energy. When a force causes an object to move, energy is being transferred to that object, which is what we call doing work. The simplified formula for work is W equals F times d, where force and displacement are directly multiplied. But keep in mind, this applies when force and displacement are in the same direction. Work is specifically defined as the product of force and displacement when the force acts on a body in such a way that the body actually covers some distance. Whenever force results in movement, work is being done. So, to summarize, work essentially measures how much energy is transferred when a force causes an object to move. Now, let's look at the third key point in this slide. When the force applied and the displacement are perpendicular to each other, the work done is actually zero. This means that no matter how much force you apply or how far the object moves, if they are at right angles, there's no work being done on the object. It's an important concept because it highlights that the direction of force relative to displacement really matters when we're talking about work. This idea ties back to our overall theme of understanding how different types of work impact energy transfer. Let's talk about how gravity interacts with work in these scenarios. When you raise a box, gravity does negative work on it. That means gravity is acting in the opposite direction of the movement, effectively taking energy away from the system. Conversely, when a man lowers a box, gravity does positive work because it's aiding the motion, transferring energy to the box as it descends. On the other hand, if someone is lifting a box, they are doing positive work by applying force in the same direction as the movement, adding energy to the system. And when a man lowers a box, he's doing negative work, since his effort opposes gravity's pull. These examples highlight how gravity can do both positive and negative work depending on whether the object is being lifted or lowered, which ties back into our overall discussion of work and energy transfer. Let's take a closer look at the angle and nature of work. This aspect is crucial because it directly influences how tasks are approached and executed. The angle refers to the perspective or orientation from which work is tackled, which can vary depending on goals, team dynamics, or organizational priorities. The nature of work, on the other hand, describes the core characteristics of the tasks themselves, whether they are routine, innovative, collaborative, or independent. Understanding these elements helps us tailor strategies that align with the specific demands of each project or role. When we consider the overall theme of our presentation, effective work management, recognizing the angle and nature of work allows us to optimize efficiency and engagement. It's about matching the right approach to the right task, ensuring that efforts are both productive and meaningful. Energy is a scalar quantity, which means it has magnitude but no direction. When we talk about energy, we're referring to the ability to perform work. In the SI system, the standard unit for measuring energy is the joule, abbreviated as J essentially. Energy represents the capacity of an object or system to do work, whether it's moving something, heating it, or causing a change. Understanding energy and its measurement is fundamental to grasping how different physical systems interact and transfer power. It's a key concept that ties into the broader theme of understanding how work is done and how energy moves through various forms in our universe. All right, let's talk about the two basic kinds of energy that are fundamental to understanding how things work around us. First, we have potential energy. This is the energy stored in an object due to its position or configuration. Think about a stretched rubber band or a raised object. It has the potential to do work because of its position. Then, we have kinetic energy, which is the energy of motion. When an object is moving, it possesses kinetic energy, like a rolling ball or flowing water. These two types of energy are interconnected and often transform from one to the other in real-world situations. Recognizing these differences helps us understand the behavior of energy in various systems, which is a key theme in our overall discussion. Understanding potential and kinetic energy allows us to see how energy is conserved and transferred, which is essential in physics and many practical applications. Let's look at some everyday examples of kinetic energy. For instance, when you fire a bullet from a gun, that bullet is moving with a lot of energy. Similarly, water flowing from a dam has kinetic energy because of its motion. Now, the key idea here is that kinetic energy is the energy an object possesses because it is in motion. We often abbreviate it as Ke. This concept is really important because it helps us understand how energy is transferred and transformed in various systems around us. Whether it's a moving car, a falling object, or flowing water, they all have kinetic energy. Recognizing this helps us see the connection between motion and energy, which ties into our overall theme of understanding energy in different forms and how it powers the world around us. Let's start by looking at the expression for kinetic energy, which is Ke equals half mv squared. This tells us that the kinetic energy depends on the mass and the square of the velocity. Next, we see an equation for work, W equals ma times v squared over 2a. Here, we're relating work to force and displacement, but to connect these concepts more clearly, we substitute the equations for acceleration and velocity. By substituting, we arrive at s equals v squared over 2a. This means that the displacement is directly related to the square of the velocity divided by twice the acceleration. We also see that v squared equals 2 as, which comes from rearranging the previous equation. Since the initial velocity u is 0, we can write v squared as u squared plus 2 as, which simplifies to just 2 as in this case. Now, moving to the third equation of motion, F equals ma. This fundamental law relates force, mass, and acceleration directly. Using this, the constant force W can be expressed as F times S, which links force and displacement to work done. Finally, the work done by this constant force over a displacement S in the same direction is W equals F times S. Putting all these pieces together, we see how the kinetic energy relates to work and force, providing a comprehensive derivation that ties motion, force, and energy, all central themes in mechanics. Now, let's talk about potential energy. The potential energy possessed by a body in a gravitational field is known as gravitational potential energy. Imagine an object like a bullet loaded in a gun or water stored in a dam. Both of these have potential energy, which means they have the capacity to do work because of their position or condition. Potential energy, in general, is the capacity to perform work due to a body's position, state, or condition. This concept is fundamental because it helps us understand how stored energy can be converted into kinetic energy or work when needed. Throughout this presentation, you'll see how potential energy plays a key role in various physical phenomena and practical applications. It's all about understanding the stored energy that exists due to an object's position or state, which can be harnessed when conditions change. Let's break down the derivation of the equation for gravitational potential energy. First, we recognize that height, or h, is a key factor here. The mass of the object is represented by m, and g stands for the acceleration due to gravity. These elements come together to give us the potential energy, which we write as Pe equals mgh. Now, since work W is equal to the potential energy in this context, we can say that W equals mgh. But to understand this more fundamentally, think of the force involved, which is the gravitational force, F, equal to mg, and the distance moved against this force, which is the height, d, or h in this case. So the work done, or W, can also be expressed as the force times the distance. Or W equals F times d. This connection is essential because it links the concept of work to the force of gravity and the displacement involved in lifting or lowering an object. By understanding this relationship, we see how gravitational potential energy depends on the mass of the object, the height it's raised to, and the acceleration due to gravity. This derivation helps us appreciate the fundamental principles behind energy conservation in gravitational fields. Let's talk about elastic potential energy. Essentially, it's the energy stored in an object when it undergoes deformation, like when you stretch a spring. This energy isn't just floating around, it's stored as a result of the deformation of an elastic object. Think of stretching a spring. It stretches and then snaps back. The energy stored during that stretch is what we call elastic potential energy. This concept is fundamental because it connects how objects deform and how energy is stored and released. It's a perfect example of the relationship between force, deformation, and energy in physical systems. So, whenever you see an elastic object being stretched or compressed, remember that it's storing energy that can be released again when the object returns to its original shape. Now let's take a closer look at elastic potential energy. As you can see, the potential energy stored in a spring or elastic object is given by the formula EP equals W, which is 1/2 kx squared. Here, k is the spring constant, and x is the displacement from the equilibrium position. When we talk about work done to stretch or compress the spring, it's important to note that work, W, equals half of the force applied times the displacement, or F over 2 times x. Remember, the force F itself is proportional to displacement, following Hooke's law, so F equals kx. This means that the average force applied during the displacement is actually half of the maximum force, which is F over 2. All of this highlights that the work done on the spring is stored as elastic potential energy. This stored energy is crucial because it enables the object to restore itself to its original position when released. Essentially, the force you apply gets stored as potential energy, which can then be converted back to kinetic energy as the object returns to equilibrium. So, in summary, elastic potential energy is the energy stored due to deformation, and it plays a key role in many systems where objects oscillate or return to their original shape. Let's start with a quick reminder that 1 horsepower, or HP, equals 746 watts. This is a common way to express power, especially in engines and machines. Another important point is that power is a scalar quantity, meaning it has magnitude but no direction. The standard unit of power is the watt, which is defined as 1 joule per second. So when we talk about power mathematically, we use the formula P equals W divided by T, where P is power, W is work, and T is time. In simple terms, power measures how fast work is being done or how quickly energy is being delivered. It gives us a way to understand the rate at which energy transfer occurs. Essentially, if more work is done in less time, the power is higher. Conversely, if work is done slowly, the power is lower. So, in any given unit of time, the amount of work performed is what we call power. This concept is fundamental because it links the idea of work to the speed at which it's carried out, helping us analyze the efficiency and performance of various systems.